Let's jump right into this explainer. Today we're unpacking something absolutely fascinating, the architectural logic of how computers create stunning digital art. We're zeroing in on the logic behind drawing data. We look at screens all day, and it's so easy to take for granted how those slick illustrations are actually built behind the glass. So let's peel back those layers and see what's really going on. Right off the bat, we run into this brilliant question. How does a computer draw a picture without using a single pixel? To wrap our heads around this, we have to completely throw out the idea of freehand drawing. Instead, picture a blindfolded robot. It's holding a pen, hovering over a canvas, and it's just sitting there, waiting for your exact, hyper-specific mathematical commands. The computer doesn't see an image. It literally only reads the data. And that brings us to the star of the show, the vector graphic. Now, I know you're familiar with standard pixelated bitmaps, those grids of tiny colored squares. Well, vector images are a whole different beast. They're built entirely from lines, shapes, and block colors that are plotted using mathematical coordinates. And because of this, they have two massive advantages. First, since they're essentially just a text file of math instructions, the file sizes are incredibly tiny. And second, infinite scaling. You can blow a vector cartoon up to the size of a skyscraper or zoom in on your phone until your thumb hurts, and it will never ever lose that crisp, clean quality. So how does this actually work? The logic breaks down into a really simple three-step dance. Step 1. You pinpoint your specific x and y coordinates on a grid. Step 2. You write an algorithm, basically a recipe, telling the computer exactly how to connect those dots. And step 3. You just step back. You let the machine blindly but flawlessly execute that blueprint to render your scalable graphic. Now, when we talk about the computer's basic grammar for shapes, it really falls into two distinct logical camps. On one side, you have polygons, which are all about that classic connect the dots logic. And on the other side, you have circles, which use a completely different approach, center and spread. Let's actually look at this shape grammar in action. Think about a polygon, like a triangle. We have to tell our robot pen to plot sequentially. We say, okay, go to x2, y1, then move to x4, y3, then drop down to x4, y1. We're defining a shape with a clear start and finish point. But for a circle, the grammar completely shifts. We don't plot the outer edge at all. We just give the computer a center coordinate, say x5, y6, and tell it to spread out by a radius of 0.5. It's wildly efficient. You're storing an entire perfect shape with just a center point and a distance. What's really cool is how this logic effortlessly bridges the physical and digital worlds. Whether you're dealing with an old-school mechanical graphics plotter dropping a physical pen onto a sheet of paper, or you're just dragging and dropping color-coded blocks in a beginner coding app like Scratch, it doesn't matter. The core underlying algorithm, it's exactly the same. But, and this is a big but, to make any of this work, we have to follow the absolute golden rule of drawing algorithms. The computer only draws when commanded. You have to explicitly tell the program pen down to start drawing. And, even more critically, you have to command pen up to stop. If you want to jump across the canvas to start a new element, you better remember to lift that pen. Otherwise, you're going to drag a messy, chaotic scribble right across your canvas and accidentally connect your rocket ship to your sun. Not ideal. So by combining those straight polygon lines with simple circle radii and being really careful with our pen up and pen down commands, we can start building multi-part objects. Take a digital blueprint for a rocket, for instance. To build it, you need a specific list of coordinates for the black triangle on the left, a totally separate list for the red rectangle in the middle, and then that center radius data for the white windows. When we stack these algorithms together, the sequence is like a choreographed routine. The computer executes it sequentially. It drops the pen for the black triangle, draws the 3 points, lifts the pen, moves over, drops the pen to draw the 4 points of the red rectangle, lifts it, moves again, and drops it precisely at the center points to sweep out those circular windows. It's just straight lines and radii coming together seamlessly. Let's push this a step further. What happens when we introduce asymmetry and repetition? Let's say we want to draw a blue car. Now, a rocket is fairly symmetrical, but a car needs a complex, asymmetrical polygon for the body paired with identical repeating elements for the wheels. The logic of those wheels is particularly elegant. The algorithm might place the first wheel at x3, y3 with a radius of 1. To make the second wheel, we just put it at x8, y3, also with a radius of 1. By just shifting that horizontal x-coordinate, we slide the position of the wheel across the grid, but because we locked in that radius at a constant 1, we guarantee the wheels are the exact same size.
It's repeating geometry, controlled by changing just a single number in the code.
Now, outlining flat shapes is one thing, but what about depth? If we're drawing the features of a bear's face, we have to start thinking in 3D, specifically Z-order stacking. You have to build from the back to the front. If you don't, that giant brown head is going to completely cover up the eyes and the nose. So you lay down a huge base layer, say a radius of 4 for the head. Then you stack a mid-layer on top for the white eyes and snout. And finally, a micro-layer for the black pupils and the nose, using tiny fractions of a radius, like 0.5. And here is where the true magic of mathematical layering really shines. Think about the bear's eye. The white part of the eye and the black pupil inside it, they actually share the exact same center coordinate, let's say x3, y6. By keeping that center completely static, but giving the white eye a radius of 1.5 and having the pupil's radius to 0.5, the computer naturally generates this perfect, nested, layered effect. It's an unbelievably efficient way to build visual complexity. To cap it all off and really bring these graphics to life, we need to add some personality. We need a smile. But a smile actually breaks the rules we've talked about so far. Polygons have to close back on themselves, and circles are fully enclosed by their radius. A smile, though, that relies on the logic of open curves. It means we have to plot distinct points and then deliberately command the algorithm to lift the pen early, leaving the shape open. It plots out so fluidly. Picture it going to x4, y3, then dipping down to x5, y2, and curving back up to x6, y3. By intentionally triggering that pen up command right after the third coordinate, boom, we get a perfect curved smile. No connecting back to the start, just a simple, happy arc. When you finally zoom out and take all of this in, it's pretty mind-blowing. You realize that all of these charming, colorful, infinitely scalable images, the rocket, the car, the bear, are literally nothing more than a highly structured list of coordinate data. It's just a stack of numbers and decimals that your device is executing flawlessly in a fraction of a millisecond, line by line, constantly lifting and dropping its invisible pen. It completely changes how you look at the digital world, doesn't it? It leaves you with this amazing question. The next time you see a beautifully crisp animation or a sleek logo pop up on your screen, are you actually looking at a drawing, or are you just looking at incredibly well-written data? Think about that. The next time you admire a brilliant piece of vector art, you aren't just looking at a picture. You are looking at pure invisible math.